Thank you very much for the introduction, ladies and gentlemen. Along with the predicted growth and demand in petrochemicals, there will be challenges coming with and also solutions required. One of them might be associated with the processing of pyrolysis gasoline. The content, growth in naphtha prediction, impact of carbon disulfide on first stage pyrolysis gasoline catalyst. We made a study there, and options how to cope with higher levels of carbon disulfide with respect to CS2 tolerance and reactor activity. Well, naphtha growth prediction for Asia Pacific. It is ethylene demand drives the need for naphtha. The gross average growth rate for ethylene has been 5 to 6% per annum over the past decade. And it is predicted to continue at the same growth rate for the next decade. And the vast majority of all growth projects will be located east of Suez, as they say. The current growth we see with the actual cracker wave in China, but also in the Gulf Coast in the US, is predominantly based on light feedstocks, gas, and dual cracker feeds. The future growth will require heavy feedstocks such as naphtha to cover also the requirements of heavier base chemicals, heavier than C2, C3, C4, and aromatics. Until 2028, about 100 million additional metric tons of naphtha are required to satisfy the demand in Asia. Naphtha demand will likely be covered by crude to chemicals projects, but also imported pyrolysis gasoline will be processed to cover growing demand for BTX. One can say, and we see the trend since a couple of years, that in general a higher level of contaminants has to be expected in the pyrolysis gasoline or in the naphtha. In particular, higher carbon disulfide levels are causing issues in first stage pygas hydrogenation. CS2 is used as a co-solvent in oil well recovery. It solubilizes elemental sulfur in rock formations, allowing hydrocarbons to flow more freely. However, it comes back to us in naphtha and in condensate feeds. And due to these properties, while processing those feeds, it accumulates in the C5 fraction, ending up in C5 extraction units, in C5 hydrotreaters, or pyrolysis gasoline hydrotreaters. What is the impact of carbon disulfide on the first stage pygas catalyst? Well, first stage pygas catalysts, they like sulfur, they need sulfur. Both nickel and palladium consist of a surface sulfided metal crystallites. Sulfur retards in general every reaction, all hydrogenation reaction rates. It improves the selectivity of first stage hydrogenation, both nickel and palladium, and it suppresses the hydrogenation of the olefins into paraffins. And unsulfided nickel and palladium hydrogenate aromatics, which is not wanted. The presence of sulfur strongly suppresses this reaction and retains the aromatics. Carbon disulfide now has a linear geometry, and due to its symmetry, it has two choices to contact to the metal surface with its sulfur atoms. It is a strong temporary poison for both nickel and palladium catalysts, and it reacts over the catalyst. So at the exit of the first stage pygas, you won't find any carbon disulfide. Well, we made a study on that, and you see here's a plot on the conversion of styrene with a typical pygas feed under typical pygas conditions. And now, if we add 20 ppm sulfur as carbon disulfide to this feed, you see after a short introduction period, a steep decline in conversion settling here in this example at about 60% conversion as the equilibrium is formed. And it is relatively stable, but on a much lower level. So you're likely running out of spec on the styrene. Well, we can do a hot hydrogen strip over a period of time, and by that, switching back to straight pygas, you recover the full activity. In the second cycle, we did the same. However, instead of a hot hydrogen strip, we increased the temperature stepwise 5, 10, and 15 centigrade to elevate the conversion back to where we came from. That works. However, if you switch then back to straight pygas, your conversion drops again and settles at a lower level. So apparently something happened to the catalyst and not the full activity is recovered. That's probably by accelerated deposits of carbon on the catalyst because we have increased the temperature. So carbon disulfide is a strong inhibitor. There's an irreversible impact without regeneration. Base activity can be restored during operation by temperature increase, and the base activity can be even completely restored to normal level after hot hydrogen strip. However, if you do nothing, there is a massive impact on your operation and you're likely running out of spec. And we even have examples, commercial examples, where spikes of as much as 200 ppm carbon disulfide have killed the catalyst within hours without the possibility to recover and to get heat into the reactor again. So what option does you have? Well, obviously a more CS2 tolerant catalyst would help and a higher reactor activity. Well, with nickel catalyst, it's quite easy. You increase the nickel activity, which is at a reasonable cost. On palladium, this is not easy, and I can tell you, simply raising the palladium content will kill you at the purchasing department. Well, higher reactor activity could be achieved by a higher specific catalyst activity, by a higher catalyst quantity, or by maximizing the catalyst inventory, the use of the catalyst inventory. CS2 tolerant catalyst. Well, we did a number of investigations and developments, and I briefly show you one on the palladium. We have two palladium catalysts, the so-called 7763 is a spherical eggshell type catalyst, and well, we moved to a different shape, to a trilobe. We kept the palladium load, but because of the higher surface area, we managed to get a better palladium dispersion on the higher surface area material, the trilobe. Therefore, the thickness of the eggshell layer of the palladium layer gets lower. And, well, by other modifications, by other ingredients, we see, at least in the test here, in the conversion of styrene in the presence of a thiol, hexanthiol, the slope of activity drop has been reduced significantly. We did further tests by exposing thiophene at different levels, as well as hexanthiol. And what we see, thiophene has not a big effect on either catalyst because thiophene is a bit bulky and doesn't really make it to the catalyst surface with its sulfur atoms. Hexanthiol has a bit a larger effect. As said, one catalyst is more receptible as the other. But the basic message is both catalysts recover. Well, if we now spark again with CS2 at a level of 35 ppm as sulfur, you see for both catalysts there is a different behavior. One catalyst reacts immediately with a decline in activity, with a decline in conversion, while the new catalyst is a bit more relaxed and settles on a higher level after the equilibrium has built out. So apparently we made some progress here to make the catalyst more tolerant against CS2. However, there is still a decline. Even it settles at a higher level, so additional measures might be requested. And this is higher reactor activity. Well, as you might know or are familiar with, our company Shell sells also high dispersion trays, which you can see on the above picture. And they enable a maximized catalyst loading because you can load the catalyst as close as 6 inches below the tray, which is a very narrow space. Typically, with other trays, you have a distance of 0.5 meter, sometimes even 1 meter. It has a high tilt tolerance, and it's customized in every single case. In the below 3 pictures, you see the difference, what it is. A conventional tray needs a pretty long way until if at all, the catalyst gets wetted. Typically, you have on top an inert layer. You get some improvement if you switch to more sophisticated bubble tray caps. However, the distance to get equal wetting is still pretty long, and you still might need inerts on top of your catalyst layer. If you switch to Shell HD trays, as said, the loading distance gets much shorter. You don't need inerts, hence you can fill in much more catalyst, and by the technology itself, it's almost perfect wetting of the entire inventory. And that's because we force the liquid and the gas simultaneously to the same downcomers. And by that, by the design of the downcomers, we force them to build a mist, a spray, immediately, which is in contrast to other techniques much more sophisticated. We have almost uniform liquid distribution. We have nearly perfect catalyst utilization. And in addition to that, it's not operating only at a single point, but in a broad range, plus minus 50% of load. You can see that on the 3 pictures below. There are other benefits associated, which I will not report here. The key message you should take with you: CS2 events are common and will be more common due to the sources of naphtha and pyrolysis gasoline. CS2 acts like a semi-permanent strong poison for both nickel and palladium catalysts. It impacts your operations, and well, it could kill even your catalyst, as you will be not at a certain level not be able to recover the activity, so not to bring in heat, your reactor cools down, and then you're lost. Well, Shell Catalyst and Technology has a strategy to tackle this. First of all, we're using a more tolerant catalyst, a more active catalyst, to delay the impact, to give our operators time to proactively adjust the process parameters. We maximize the reactor activity by using the Shell HD trays in all of our reactors, and by that enable maximum catalyst loading. And as a given fact, due to the design, the HD trays display a nice technology producing a spray, and by that you get immediately wetting of the almost entire inventory, and by that you making maximize use of your catalyst inventory. And we have examples that by doing that, switching to our catalyst, installing the reactor internals, your capacity could be improved by as much as 30 or 35% compared to the situation before. I think I'm well ahead of time, so I get a benefit probably from that. Thank you for your patience, and thank you for your audience.